Perfect.
Cool.
Yep.
All right, I think we can get started. So it's a pleasure to welcome back Dr. Mike Grudick today. And so as I think probably all of you know, Mike was a Hubble Fellow here until 2 months ago, I guess. He's since then moved to the Flatiron Institute, where he's an associate research scientist, so a great new position. So Mike's work really focuses on understanding star and galaxy formation, in particular the process of star formation itself. He did a lot of work while he was here on really trying to figure out the physics that sets the initial mass function of stars, which is obviously a long-standing, challenging problem, and made some really impressive inroads into that. And yeah, he's going to tell us about some of his work today, in particular how feedback regulates the universe. So take it away.
All right, thanks, Andrew. Hi, everyone. Thanks for coming. It's great to be back and see you once again, and finally get around to giving you this talk. You know, I was going to do it back in May, I think, but got sick that day. So hopefully I won't get sick within the next hour, and we'll get this done. Otherwise, you'll see me again. Right. So I don't really like long talks, so we're not going to do a long talk. We're going to do 4 short talks. So part 1, I'm just going to kind of talk about the background of where I'm coming from with a lot of these problems I like to think about regarding star formation, stellar feedback. Part 2, I'm going to tell you about my sort of main gig, which is the STARFORGE project, this simulations collaboration that we've put together over the years. Part 3, we're going to talk about the initial mass function and talk about what physical processes I think are responsible for setting it and what we might expect to see in different environments. And in part 4, I'm going to tell you just about a bunch of cool stuff that we're going to be doing either working on right now or in the future in the STARFORGE project. So let's start from the standpoint of galaxy formation. So you all know the basic picture that you have all of these dark matter halos that form, gas falls in, gas turns into stars, and you get your galaxies. And of course, we can count up very well how many dark matter halos of a given mass we expect to see. It looks something like this sort of Schechter function. And then the kind of most naive expectation for how many galaxies of a given mass you'd expect to see would just be this. Just take the halo mass and multiply it by the cosmic baryon fraction. Of course, that is not what we see. We see something that looks more like this. Again, very, very sort of qualitatively, not to scale, right? So there's this big discrepancy between the number of galaxies you'd expect to see at a given mass, both at the high and low mass end of galaxy formation. And the general paradigm for explaining this is that at the high mass end, the engine that has to regulate the amount of baryons you can put into galaxies is active galactic nuclei, which I'm not going to talk about much today. I don't know much about that. What I do know something about is stellar feedback, which is expected to be the main agent responsible for regulating galaxy formation, sort of at Milky Way mass and lower. So what is stellar feedback? Well, it comes in a whole bunch of different forms. One of my personal favorites, often less discussed in galaxy formation context, but I think still quite important, as we'll see, is protostellar outflows. So basically, whenever you look at a star-forming region, you see these bipolar outflows, and it's been possible recently to image these in exquisite detail, showing all of this molecular emission in the infrared with Webb. And what's going on there is you've got these accreting protostars where the gas is coming in, it's getting close to the star, but the way the structure of the accretion plus wind flow works out, you don't end up accreting 100% of the gas that falls in close to the star. A fraction of it gets launched in these bipolar outflows. You've also got stellar winds, and stellar winds from massive stars in particular can be a very, very energetic source of feedback because these things are going at thousands of kilometers per second, and the mass loss rates of stellar winds can be quite high. So if this energy can be converted into work, then it can also do a lot of damage and drive powerful wind-driven bubbles. You also have radiation from these massive stars, which is going to do a number of things. It's going to heat up the gas. For example, it's going to ionize gas, heat it up to order 10,000 degrees Kelvin, create these overpressured regions which expand, and you get H2 regions. And it also exerts radiation pressure. So when it gets absorbed, that photon imparts a kick, and that effect can also contribute to blowing apart molecular clouds. And last but certainly not least, you have supernovae. So supernovae are probably the main source of feedback energy, responsible for regulating the properties of the interstellar medium in galaxies and the overall star formation rate and launching of galactic winds. So there have been a lot of calculations performed for galaxy formation where you have this cosmological setup, some dark matter plus baryons in a box, they form some galaxies, and then if you put in the right prescriptions, then you can come up with feedback prescriptions that get you a reasonable answer for things like how many galaxies of a given mass you have. This is a compilation from a recent, well, I guess not so recent these days, review of these various cosmological simulations. But of course, if we actually look at what the interstellar medium looks like, for example, as it has been recently possible with Webb, there's all of this exquisite detail going on here, and these sorts of cosmological calculations are more or less resolving things at this level. So there's a lot of stuff going on that we're not capturing just in kind of typical cosmological simulations. And this gets us to why cosmic structure formation in general is hard, right? So the curse of dynamic range. Galaxy and star formation is an intrinsically multi-scale process going from tens of megaparsecs and upward down to individual galaxies of a few kiloparsecs to molecular clouds, 100 parsecs, star clusters, 1 parsec, and all the way down to the individual stars. And the tricky thing is because you've got feedback, if you screw it up at the smallest scales, then that error is just going to propagate back up to larger scales. So you really need to have some sort of picture of what's going on at this entire range of scales in order to get the right answer. And self-consistently, that is just not really possible with numerical simulations. If you're going to do a simulation, you get to pick basically a certain dynamic range that you can do. I'd say the state of the art would be a factor of like 10 to the 6. And on smaller scales, you just have to have subgrid physics. And on larger scales, you have to make some assumptions about your initial and boundary conditions. And of course, you can do different simulations that focus on different segments of this dynamic range. And the game here is to really bootstrap our understanding of this big picture from kind of gluing together what we understand from these various segments that we're able to model self-consistently. Yes?
In this size of the dynamic range that we can simulate over time?
Yes, there has. I mean, I feel like some of these, for example, AGN zoom-in type works we've been doing, for example, they're pushing more to like factor 10 to the 7, whereas like previously it was 10 to the 6, and there are various other similar calculations going on. So that number is always going up because computational capacity is always getting better, but like we're not going to get this whole range right for a long, long time just at that rate, of course. So we have to try and do clever things, unfortunately. Right. So around the time I was getting into the field, there was this new generation of cosmological zoom-in simulations of galaxies that had a higher degree of resolution than the sort of standard cosmological simulations. And they were able to resolve all the various phases of the interstellar medium, as shown in the different colors here. And these sorts of simulations were very encouraging because they got a lot of things right, essentially for free, that previously had to be put in by hand. Things like the Kennicut-Schmidt relation, thin disks. Oh, we having a... Yeah. There it is. Right, so this generation of galaxy simulations got a lot of things right for free just by trying to do the physics self-consistently, and these scaling relations we wanted to get right just kind of emerged from that. So that was cool, but we wanted to do more. And in particular, I wanted to know about star clusters. I want to know why in the solar neighborhood, the most extreme example of a star cluster, young star cluster forming is Orion, which is 10 to the 3 solar masses. But we see these things floating all around the galaxy, which probably at some point in their life were more than 10 to the 6 solar masses. Why doesn't the Milky Way make these anymore? What fraction of star formation goes into these things? How many of them are there of different masses? And what can these ancient things floating around our galaxy tell us about what our galaxy looked like when it was very young? So these sorts of things. So to do that, you need to model not just the galaxy scales, but the star cluster scales. So the kind of current state of the art for that is doing these sort of isolated giant molecular cloud simulations. I did a lot of these during my PhD thesis work. So these have generally been 10 to 100 parsec scale setups, resolving scales on the order of maybe 1/10 of a parsec. And they've been able to account for various different sorts of feedback physics acting in concert. And you tend to get a sort of picture like what's going on in this movie here, where the cloud collapses a bit, then you form some stars, and then the whole thing blows apart, and you can measure the outcome of star formation. And a lot of these calculations actually agreed on certain basic things, at least qualitatively. For example, pretty much everybody finds that as you scale up the surface density of your cloud, you start converting a larger and larger fraction of your initial gas mass into stars. So the star formation efficiency increases with surface density, and it's fairly straightforward to justify that just kind of back of the envelope. It's pretty much that stellar feedback just doesn't work at these really high surface densities, and gravity wins against feedback. And we've also been able to find some, again, qualitative consensus on things like what fraction of the stellar mass actually goes into bound clusters. And that's been anticipated for a long time, that it should increase with the star formation efficiency, because basically if everything's converted into stars in situ, then it just kind of stays together. Whereas if star formation efficiency is low, then most of the binding energy comes from the gas. So once the gas is gone, it flies apart. But you can see there's a lot of scatter here. So there's kind of qualitative but not necessarily quantitative agreement between the models. But everybody seems to agree that feedback is crucial for setting the star formation efficiency in these clouds, radiation from massive stars in particular, and star formation efficiency depends on environment via this scaling with surface density. And higher star formation efficiency gets you more massive and more bound star clusters. But when you look at this in detail, the tricky thing is that none of the calculations I've shown you so far are actually modeling individual stars that form in these molecular clouds. They're using some sort of subgrid prescription for what stars should form in what region of the simulation, without actually resolving the gas flows that actually assemble these stars. And you can ask, okay, well, maybe it's robust to our choice of subgrid prescription, and it doesn't matter for the star cluster scale stuff. But it turns out it does. So these are 6 examples of instances where people have looked at diagnostics of either the dense interstellar medium in their simulation, or the fraction of mass going into bound clusters, or the cluster mass function, or the star formation efficiency, all these different sorts of things. Anytime somebody plays around with their model parameters for their subgrid star formation, they always find that the quantity of interest on like GMC and star cluster scales tends to depend quite sensitively on what they're assuming. So what that tells us is that these sort of 10 to 100 parsec scale cloud simulations that had been done thus far, they were able to explain certain aspects of star cluster formation and GMC evolution, but at the same time we were hitting a wall, this sort of fundamental limit in our predictive power, because we just don't know how to model star formation subgrid. So that's where STARFORGE comes in. So historically, star formation simulations had been relegated to kind of 2 opposite regimes, where there were people for a long time, in fact, resolving every single star that forms in the cloud, but typically in sort of smaller scale setups. So with a total gas mass of less than maybe 10 to the 3, whereas most stars are probably forming in clouds upwards of 10 to the 5 solar masses in the Milky Way. And some of these even accounted for a sort of limited subset of the feedback processes involved. but they were able to say things about, for example, the IMF in these small-scale experiments. And then there was this opposite regime, which is the stuff we already talked about. So these sort of larger scale, 100-parsec scale simulations where you're following the global evolution of the giant molecular cloud, but you don't have all those fine-grained details of which star should form where, and you're modeling that subgrid. So what we wanted to do was put together a simulation where we are forming individual stars as self-consistently as we can. We're including all of the important feedback mechanisms acting in concert, which had never been done before, something that can scale up to sufficiently massive giant molecular clouds to be kind of representative of the way star formation usually plays out. And we also needed something that was efficient enough to actually run to the end of star formation, start to finish, which typically is on the order of 10 million years in molecular clouds in the solar neighborhood. So that was kind of the wish list that informed our design requirements for STARFORGE. So what is STARFORGE? So it is a numerical framework implemented in the Gizmo meshless MHD code, using Gizmo's MHD method as kind of the backbone algorithm that we build everything on top of. So it's a Lagrangian method, so you're following these mass elements around according to the equations of motion. The sort of unique thing about STARFORGE is it was the first simulation setup to combine all of these different processes that we think are important in star formation acting in concert. We implemented n-body dynamics with a higher order integrator. We follow individual star formation, a host of cooling and chemistry processes, not like state-of-the-art chemical networks, but enough to more or less get our temperatures right. And for the first time, we incorporated all 4 of these major stellar feedback mechanisms: jets, winds, supernovae, and radiation. So to put protostellar jets into the simulations, we use a subgrid model. So that, essentially, that's where our subgrid comes in now, is we have a star in the simulation, and we have to decide how much mass goes into the wind or jet that gets launched, and how fast does the jet come out. And we do this according to this essentially phenomenological model with 2 parameters that determine these respective fractions. We track radiation in 5 different bands from the far and extreme UV all the way to the mid to far IR. And all of these different bands kind of do different things in star formation, from heating the gas up to imparting radiation pressure. And you really do want to kind of account for each of these effects individually. These are radiation MHD simulations where we are directly evolving the radiation field in the code. We model stellar winds with a set of prescriptions for essentially how much mass, metals, momentum, and energy the stars should be injecting. It's a simple phenomenological prescription again, where we account just for the Wolf-Rayet phase when it comes to stellar evolution. That's when the winds get really strong. And it's kind of an adaptive method where you're just injecting these quantities kind of locally into nearby particles if we can't directly resolve the wind structure. But if the gas is diffuse enough, we can actually resolve the structure of the wind bubble self-consistently from the free expansion radius outward. And when that is possible, we do so by just directly injecting new mass elements into the simulation and just putting the wind in by hand, essentially. And lastly, we implement supernovae just by assuming that every star greater than 8 solar masses undergoes a 10 to the 51 erg supernova at the end of its life. And for the supernovae, we directly resolve the ejecta always. So again, we're putting in these new Lagrangian mass elements and following them outward into the supernova remnant. So just to give you an idea of what one of these simulations looks like, this is a movie of our first simulation we fired off with this full physics setup. So this is a 10 parsec cloud. It's got 20,000 solar masses in it. Just initially uniform density with a uniform magnetic field, but a random turbulent velocity field. And it's that random velocity field that seeds all of the sort of chaotic turbulent collapse motions that end up going on to seed the formation of individual stars. So you form these dense clumps, these dense filaments that eventually go on to be gravitationally unstable. and collapse. Once collapse has reached a certain point, we replace the gas with a sink particle, and the sink particle sucks up the rest of the gas that's coming in. And then as these stars accrete more and more, they're launching jets. Some of them get massive, and they open up H2 regions and wind bubbles around them. And as star formation proceeds, you get more and more stars around, which means more and more feedback, until eventually the cloud just can't take it anymore and it starts blowing apart. The collapse starts to reverse, and star formation starts winding down because there's less and less dense gas around as you're just kind of blowing the whole system apart. And eventually we get our first supernova going off towards the end of the simulation, and that kind of puts the final nail in the coffin. At this point, there's pretty much no more ongoing star formation. But what we've done here, which again hadn't really been done before, was simulate star formation just from start to finish. So collapse and then feedback, and then entering the sort of gas-free phase for the star cluster. And when you do that, you can actually study the properties of the star cluster you get and do lots of fun stuff. So that's the idea of STARFORGE. Were there any just general questions about STARFORGE before we move on?
Like, why hasn't this been done before? Was it a technological aspect that was new, or kind of coding?
Yeah, it was just really hard. It's putting all of these different things together in your simulation and making them talk to each other in a way that is accurate and numerically stable. And it basically took like myself and my colleague David Gusenov pretty much working full time on this stuff for a couple of years before we started getting nice results. So it was kind of, it just took a while for those circumstances to fall into place. And Gizmo is also kind of a nice efficient code that has various advantages for these sorts of problems, and that's, I guess, relatively new as well. Dan?
Just to clarify, I think this is amazing, and the fact that you were able to only do it in 2 years seems like that was super fast. Kind of watching from the outside, because it is I mean, people have been talking about this for decades, right?
Yeah, I mean, I got a good deal out of the pandemic. I think, I basically didn't have anything else to do than get this stuff working. Dan, you had a question?
I'm going to be obnoxious and say I really only have a comment, which is, I mean, this is really amazing, and it reminds me of something Phil Pinto told me about 5 or 6 or so years ago. I was in Arizona giving a colloquium about the whole, 1/f noise, star forming main sequence stuff, and lots of people had questions as to why does that do better than the simulations, the galaxy formation simulations. So Pinto, he works on supernova explosion, right? So he figured out, he was just like, it's obvious, right? You can't simulate 1/f very easily, right? It diverges. You just can't get that kind of, you can't simulate turbulence very well. But I see this, I look at this, and I think, you mean you really cracked something? And that's my comment. This is amazing.
Yeah, maybe. I'd say, the 1/f thing, that's initial conditions for this, essentially, and
right?
yeah.
All the range of scales that you show here, following it.
Yeah. So I'd say the big caveat is our initial condition is this silly looking gas sphere, and we want to do better at that, right? But yeah, the important thing is at least we're putting in all the physics that we think might matter. All right, let's talk about the IMF. So the IMF is something that comes straight out of these simulations. We just get a mass distribution of these stars that we're forming. So I don't need to explain the IMF to all of you, but there's this distribution of different masses that stars can have. Stars can be very massive, they can be very low mass. Typically you get M dwarfs out of star formation. You can compile a lot of different measurements that have been made. This is from a recent review we put together. And what we're plotting here is the IMF slope as a function of the mass range in which it is measured, indicated by the horizontal lines. So your salpeter slope is along here, and we're plotting the sort of typically assumed standard IMFs like Krupa and Chabrier on this diagram. And there's a couple of interesting things to note. One is that they're not all perfectly on a line or a locus. right? So maybe there's some variation, but clearly there are error bars, so those might contribute to the scatter. So it's this sort of big, interesting question, are there IMF variations? How big can they be? People typically call the region where this slope passes through zero the peak, so that's that sort of modal M-dwarf outcome of star formation, and this tends to be particularly tight on this diagram. It doesn't seem to vary a lot when people go and measure it. But something worth noting is that there are examples of systems where the measured high mass slope is significantly shallower than the standard assumed saltpeter, and these tend to be in just the most extreme regions where the IMF has actually been measured, such as 30 Doradus and the galactic center, so very high densities. So that might mean something. We'll come back to that. Another thing I'd like to point out is that there may be a high mass cutoff. There may not. The physics behind it has been poorly understood, and we just don't have enough samples to really say very much about it. So you just kind of have to assume a high mass cutoff, like people like 120 or 150, things like that when they're doing population synthesis. But we don't really know what this should be. So how do we make an IMF? Well, one possible starting premise is just to assume that the dense interstellar medium is isothermal. So why would you do that? Well, this is a sort of widget I put together called the IS emulator. And it lets you play around with these different ISM cooling processes, switch stuff on and off. So this is temperature as a function of density. But the key thing is that once you get to high enough density, the gas collisions with dust grains are so frequent that the gas and dust temperature just become the same. And that dust temperature is just set by how much radiation is around. So you get this sort of isothermal regime. So is that enough to get us an IMF? Well, Fred Hoyle thought no. He thought about what would happen if you have a self-gravitating isothermal fluid. And basically, he described the scenario as a kind of gravitational turbulence where you have structures forming, but they don't disperse. They want to collapse even further and then fragment again and again and again and again. So sort of catastrophic fragmentation. And it turns out that is exactly what we see if we try and simulate this scenario. So if we just have isothermal gas plus gravity and ask what IMF comes out of that, we get something that depends entirely on the mass resolution that we assume for the simulation. In other words, we do not achieve numerical convergence in the IMF if we just have these two ingredients. And this is not just us doing this with Gizmo. This is all these different groups that have tried this type of setup. And to my knowledge, a converged IMF has never been demonstrated based on just these physical ingredients. So you need something else to get an IMF. Well, what about magnetic fields? Well, we basically did the same sort of set of experiments with magnetic fields switched on, so isothermal gas plus MHD plus gravity. And we actually got something that looked kind of converged we still never really got much of a low mass cutoff converged, but like if we at least picked a range above 1 solar mass and just asked how much does that vary with resolution, it actually turned out to be pretty converged. But of course, the issue then was we had this really sort of kind of flat, weird-looking, top-heavy thing that doesn't really look like the observed IMF. So we got something that was maybe an IMF, we believed, but was not the observed IMF with this formula. So regarding the low mass cutoff, well, it turns out that you can't actually continue isothermal collapse to arbitrarily high density. So eventually you're going to reach a point where the radiative transport time is longer than the freefall time, and the temperature is going to start to rise, and essentially dust emission can no longer radiate away the energy of compression and collapse. And when that happens, your Jeans mass, which was initially dropping with density, will start to rise again. So you get this kind of minimum Jeans mass that may imprint a sort of minimum stellar fragment mass that you can get. And we recently worked this out in sort of a greater level of detail than had been done before. And the minimum Jeans mass you get from this is actually a very weak function of dust opacity, which is we can kind of conflate with metallicity. you know, it may be kind of nonlinear, but basically it should be very robust to metallicity in radiation fields like we see in the solar neighborhood, like 1 eV per cubic centimeter. But as you turn up the radiation field, you actually get a stronger scaling with dust opacity and or metallicity. So can that get us an IMF? My colleagues over in France fired off various simulations where they modeled the opacity limit with just a barotropic equation of state, did the same sort of thing where they count up how many fragments they get of different masses. And they actually found that that was sufficient to get an IMF that actually looks quite a bit like what is observed. I wanted to see if I could reproduce this with my gizmo setup, so I did a similar sort of thing where I put in different equations of state, where I varied where the opacity limited Jeans mass actually occurs. So each curve here is a different equation of state where I'm varying either the low density temperature or the density at which you start going adiabatic, which sets the minimum Jeans mass. And for the right parameters, again, I got something that looked quite a lot like, for example, a Chabrier IMF. But this was for a very dense clump, something about 2 orders of magnitude denser than anything we see forming stars in the solar neighborhood. Once I simulate a solar neighborhood GMC, then again, I get this sort of relatively flat or shallow, top-heavy thing that has way too many massive stars and doesn't really look like the IMF. So again, we're coming back to that problem we already had. So we have this opacity limit still setting the low mass cutoff, but you need something extra to regulate the high mass end. And what is that thing? Of course, it's feedback. So our IMF story so far is basically as follows. We had this sort of shallow, top-heavy thing with isothermal MHD. If you do a better job of the cooling and chemistry and get things like the Jeans mass right, you still get this really shallow, top-heavy thing. But actually, once you switch on protostellar jets, you start regulating the accretion flows around individual stars, and you start getting something that actually looks a lot more like the observed IMF in terms of both where it turns over from the power law and the actual power law slope. But this is for a model of a GMC in the solar neighborhood, and it still formed a like 400 solar mass star that was still accreting at the end of the simulation. So what else do you need? Well, you need the rest of the feedback. So the radiation and the winds from the massive stars actually prevent those massive stars from growing too much. So you end up getting something that looks like pretty reasonable across the entire range of the IMF. So basically, our picture that we're seeing from STARFORGE is that protostellar jets play an important role in regulating the accretion flows that feed individual stars, and that will determine the sort of turnover from the salpeter power law, which sets your typical stellar mass, your typical M dwarf. As we saw, we think the opacity limit sets the low mass cutoff. We're not actually resolving that in these data here, but we saw from these previous experiments. And at the high mass end, you need the radiation and the winds from the massive stars to regulate the high mass tail. Yes? Yeah, sure. So you have a sink particle that is accreting gas, and a certain fraction of the gas that gets accreted is diverted into the jets. We set that to 30%. And those jets are launched at a certain fraction of the escape speed from the protostellar radius. So that's square root GM over R. And that fraction is also fiducially set to 30%. And these are parameters taken from previous works, basically trying to reproduce the inferred momentum loading of observed outflows. So it's kind of phenomenological in a sense. Right. So we've explored various facets of the IMF in these various works shown here. But I got really interested in the upper cutoff of the IMF. So in particular, you have this power law part, and is the variation in the most massive star in a cluster just due to sampling further up this purely self-similar power law, or is there some sort of cutoff? So what I did is I ran 100 low mass clusters, and their stacked IMF is shown in black here. And what I found was that the high mass cutoff, or the most massive star you see in a cluster, is not just a size of sample effect from sampling pure power law. There is a physical cutoff here that we see in the distribution that we get. Moreover, this cutoff is set by feedback physics. And we know this because we also simulated one cloud without feedback physics, and it formed much more massive stars. Moreover, it depends upon cloud properties. So where your high mass IMF cutoff lives is going to be determined by the local conditions. So things like mass, surface density, metallicity, et cetera. And we saw this because just comparing with our one high mass cloud, that one high mass cloud formed a star more massive than our 100 low mass clouds, despite the fact that the 100 low mass clouds had 10 times many stars total. So that's kind of interesting, but it's really not such a crazy thing if you think about it. So you can ask, given a star-forming clump of a certain mass and surface density, how much feedback do you need to blow that clump apart within one freefall time? So basically, whatever type of feedback you like, you always get a similar sort of qualitative answer. So for momentum feedback, like radiation or radiatively efficient winds, you require a momentum input rate that scales as a positive power of mass and surface density. For energy feedback, again, a positive power of mass and surface density. And for photoionization, again, same story. So in other words, the more massive and dense your clump in this idealized setup, the more feedback you need to blow it apart, which means it would have to make a more massive star. Now, obviously, it's a huge leap to go from this very simplistic picture to an actual star cluster in IMF. But that's the basic physical principle, that feedback works to varying degrees in different environments, and that should imprint something on the initial mass function. Denser, more massive clouds can tolerate more massive stars without being disrupted. There's also another interesting effect that we expect from radiation pressure on dust grains. So very massive stars are basically pinned at the Eddington limit determined by the Thomson cross-section. And you end up getting this mass-luminosity relation that very massive stars lie on. Now, the main opacity in the flow that is actually feeding these stars comes from dust. And we expected this to scale in some way with the metallicity. So we can define this metallicity scaled, or this essentially dust-scaled metallicity parameter that determines the opacity. Now, if you write down the ratio of the radiative to gravitational acceleration in this scenario, then you just get something that is a pure function of this dust-scaled metallicity parameter. And what this tells us is that if we plug in 1 for this ZD, in other words, just solar neighborhood dust, then the radiative pressure force is 20 times stronger than gravity in this idealized scenario. So does that mean massive stars just can't form in the Milky Way? No, they do, but the gas has to do fancy things to reach the star. It has to come in a disk or in streamers, and it's not so simple. But if we go down to something like less than 5% solar metallicity, then this becomes order unity, and it less than order unity, and radiation pressure on the dusty neutral gas feeding the stars just stops working. So that kind of suggests to us that there may be some sort of interesting transition in the way that the flows feeding massive stars get regulated as we go to low metallicity or dust poor regions. So we can see how this all plays out in a recent calculation I've been working on publishing. So this is another 20,000 solar mass cloud, but now we've scaled up its surface density by a factor of 100 compared to what we did before for Milky Way conditions. And we also scaled down the metallicity by a factor of 100. So this is a 1% solar metallicity cloud, and the dust abundance is scaled accordingly. And this actually gave a pretty startling result. So this simulation produced a maximum stellar mass of about 1,800 plus 3 other stars in excess of 1,000 solar masses in a quadruple system shown here. Eventually, the combined stellar winds from this very massive stellar system just blow the whole cloud apart catastrophically in a 100 kilometer per second wind-driven outflow. And if you look at the IMF that comes out of this, then it is quite top-heavy compared to a standard Chabrier IMF. And of course, you've got your 4 very massive stars up here. And your essentially rest frame UV light to mass ratio, that would determine, for example, how much star formation you're inferring at high redshift, something like that, is actually elevated by a factor of about 10 compared to a standard stellar population. So there's just a ton of UV coming out of this IMF, particularly because of these very massive stars. And the existence of such massive stars may also have very interesting implications for things like the UV luminosity function at high redshift. People like to think about nitrogen enrichment with very massive stars. And also the seeds of supermassive black holes. If they can actually be this massive, then that might change some things. So that it may be interesting. I got interested in understanding how the mass actually gets to these very massive stars. So this is all of the gas in the simulation. This is the gas that fed the most massive star, Paul. This is the reservoir that fed John. This is the one that fed George. And this is the one that fed Ringo. So you can see that there's actually a lot of overlap here, right? So these stars are kind of feeding from a common gas reservoir. They form separately initially, and we can look at the way these form. But as time goes on, you'll start to see a lot more similarity in the structure of the flow around these stars, and they'll first pair up, and then those two pairs that paired up themselves paired up to get your quadruple system. But what ends up happening is basically you're accreting an order unity fraction of the total mass of the cloud into just these 4 stars without catastrophically fragmenting it. And we look at the way that the accretion rate varies as a function of stellar mass. We can see that they all do a very similar sort of thing where they accrete faster and faster and faster as they get more and more massive, kind of qualitatively like a Bondi-Hoyle accretion expectation. But it turns out that the dominant scaling in this is actually something like m to the 2/3 power. So if we pull that out, we just get a flat line here. And that's kind of interesting because that was anticipated from a scenario of tidal lobe limited competitive accretion. And that's essentially where you have a few stars that are being fed by a common gas reservoir, and they each accrete in proportion to the size of the region that they dominate tidally. The size of their Hill sphere, essentially. So in other words, the mechanism for this very massive star formation at low metallicity is from runaway accretion, which I thought was pretty surprising because typically when people talk about top-heavy IMFs at low metallicity, they talk about having less coolant around and a higher Jeans mass, but it's not the fragmentation, it's the accretion. And we can kind of break down what different mechanisms are important for regulating the mass of the most massive star here. So that simulation I showed you, a segment of it is shown in purple here. I think that Grootage 2024 is pretty optimistic at this point, but soon, I promise. Whereas our fiducial solar metallicity cloud with the same bulk parameters formed a star of about 150 solar masses. Now, we switched off infrared radiation pressure in that solar metallicity cloud, and we found that the star could just keep on accreting. So clearly, that dust radiation pressure is important. We also turn up the wind mass loss rate by a factor of 3, and we got a less massive primary star. So winds are also clearly part of the equation in determining how much stars can accrete at solar metallicity. So it's all of these different processes acting in concert at solar metallicity. But again, winds are much weaker, and dust radiation pressure is much weaker at low metallicity, so you get this runaway growth. So just to break down kind of my picture in my head of what the anatomy of the IMF is, and then this part of the talk, you have your low mass cutoff that's set by dust radiative processes like this opacity limit picture. You have your turnover to the salpeter power law part, and that's going to be determined by the properties of turbulence in the cloud and regulated by protostellar outflows. You have your high mass slope, which could in principle be determined either by fragmentation or accretion physics. These various works have found in favor of either camp, but as we've seen, there's clearly a lot of accretion going on in STARFORGE. And you have your high mass cutoff, which is set by the radiation and wind feedback from massive stars, and that may work to varying degrees in different metallicities. All right, so to wrap up, I'm just going to tell you about some cool stuff that we're working on and in the collaboration. So one fun thing you can do with these simulations is we can say, hey, we have a simulation that has all the necessary ingredients to model molecular clouds in the Milky Way, and then we can compare the simulations with observations. So these are two projects undertaken, one by an undergraduate, Sam Millstone at UMass, comparing gas maps taken with Herschel with young stellar object catalogs taken with Spitzer. And then we actually followed this up this previous summer with a CASI student, Alex Escamilla, who took it a step further and measured the star formation efficiency in these clouds in the same way as was measured by the observers. And what Alex found was that we got this really interesting evolutionary trend. So the different colors showed different stages of evolution in the cloud. And as it turned out, this variation is quite comparable to the variation we see in observations. So we thought that was cool, and we're probably going to be writing that up in some form. If you're doing these sort of mock observations, you can also combine that with machine learning to solve some fun inverse problems. So my colleague Duo Zhu is kind of the world expert on this type of game. So what he did was make dust emission maps, and he trained a model on the simulation such that given a dust emission map from Herschel and or Spitzer and or Webb, you can back out the radiation field within the cloud, which of course is related to the dust emission that you get, but in a sort of complicated way, but his neural net can kind of figure it out. So I thought that was pretty neat, and there's lots of other stuff you can do like this with the simulations. You can use the STARFORGE simulations as the initial conditions for longer-term evolution of star clusters and actually follow the way the star clusters evolve dynamically and disperse in the galactic environment. This was a work by my colleague Juan Farias at UT Austin. And you can also use this sort of numerical laboratory as a baseline for exploring new physics that we hadn't accounted for yet. So I can highlight 3 different projects undertaken by various PhD candidates, or Margot is now Dr. Margot Fitzaxon. So she looked at the effect of self-consistently transported cosmic rays in the clouds. So she fired off the first numerical simulations of star formation with self-consistent cosmic rays, not just assuming a uniform background, and found some interesting things. Nina Filipova, another student at UT Austin, she's been looking at the effect of non-ideal MHD in the structure and formation of protostellar disks. And Nadine Solomon, just down the road at Caltech, has been looking at the effect of dust dynamics upon star formation and things like radiation pressure on dust and stellar abundances. And it's kind of cool because all these things are actually really intimately connected, and we need to understand these different physical processes if we want to actually probe to these smaller and smaller scales, like on the scale of disks, because your cosmic rays will determine your ionization. The structure of your accretion flow may produce accretion shocks, which produce cosmic rays, and you get grain charging, which will determine your non-ideal MHD coefficients, and also dust dynamics that will depend upon the structure of these disks. So this is all just one big frontier, really, probing to these finer and finer scales and coming to grips with these additional pieces of physics that we had previously neglected. And lastly, I just want to talk about kind of scaling this stuff back up. So I never intended to kind of go down the rabbit hole to small scales and IMF stuff. I was always kind of thinking about doing stuff in the context of galaxies. And as I mentioned, we don't really like our initial conditions. They're just these silly gas spheres. We'd like to inform things with an actual self-consistent galaxy model. So we did something kind of like this in this recent series of papers where we did these zoom-in simulations, starting with a galaxy, and you just apply a certain refinement criterion around the AGN in the galaxy, and you can resolve the structure of the disk around the AGN. And we'd like to do something similar for example, molecular clouds forming a star cluster in a galaxy. We'd like to just take the galaxy and apply some refinement in the right sort of way so that we can just do the star formation more self-consistently, informed by the larger scale flow that would have inevitably had some continuity with the dense cloud that forms the star cluster. So this is underway being led by Siobhan Kular, a PhD student at University of Toronto. And we're working on kind of getting the numerics dialed in on this right now. But the idea is, we want to kind of put this in a larger galactic context. And another way you can do this is take what we've learned about star formation on small scales and calibrate that into a new subgrid prescription for star formation. So, we have all these different properties that we can measure from the STARFORGE simulations and in principle train a new model that populates stellar phase space in a more physically informed way than has been done before. And that's another way that I would like to kind of scale what we've learned up to the galactic context. We'll skip that. All right, so to summarize, we've sort of explored how the objects that make up our universe, whether you're talking about galaxies or star clusters or individual stars, are all sculpted by feedback. And I think we're really just scratching the surface of how this works, again, because of this sort of curse of dynamic range and how it's kind of hard to really have the whole picture together self-consistently. But what STARFORGE has done for us is give us a sort of numerical laboratory where we can study the effects of different processes active in star formation and make a little bit of progress disentangling the different things that go into the IMF. And there's a lot of fun stuff that we can do on a variety of scales, from protoplanetary disks all the way up to galaxies. And we can also use these nice models to get novel interpretations of existing observations. So stay tuned. Thanks.
More questions? Dan was eager.
So I think these experiments you've done are fantastic. They look amazing. And I think my question is it has two parts. You can pick what you want, which is going back to this context within galaxies. There are sort of two directions. One is, as long as you're getting reasonable results for initial mass functions in regions, does that suggest that the current feedback prescriptions and subgrid physics recipes within, say, FIRE or FIRE2 just aren't right from that perspective? Or going the other way, we know that the FIRE and FIRE2 simulations have star formation histories in their galaxies that are too bursty compared to what they are like in the real world. Do you then, is there something in the other direction that tells you that when you try embedding what you've learned here within those contexts, do you worry about a mismatch then with just the wrong kinds of initial conditions for the clouds based on them being too bursty within the context of their histories? So
yeah,
you pick what you want, I guess.
Yeah, great question. So yeah, it's interesting to think what are we missing out in something like FIRE? So for those not familiar, FIRE simulations coarse grain the gas in the galaxy to usually something on the order of 10 to the 4 solar masses in one gas cell. And what are we missing in terms of the substructure on smaller mass scales than that, which is basically where STARFORGE starts. And I think it could be various things. Like, for example, there could be, again, these sorts of IMF variations as a function of the environment. Those are not accounted for by any current galaxy formation model, including FIRE. It could be effects in the way that feedback actually couples. For example, when you worry about stellar winds, you actually find that you need really, really high resolution to actually self-consistently model the transport of energy out of the wind bubble. So you can't really do that at low resolution. And just this whole interplay between the different feedback processes that's happening on these sorts of smaller mass scales, nobody has a model that explicitly captures that subgrid. It's not fully understood. I can imagine that when we get to the burstiness predicted by the simulations, one component of that is the subgrid star formation prescription, actually. If you basically make it so that a lot of gas has to pile up before you get stars, then you're going to get a big bang after in the feedback, and that can drive burst cycles. So it may be that maybe there's some more correct prescription out there that may change the result, and assuming there is a disagreement with the observed degree of burstiness, it may mitigate that to some degree, I think. Yeah.
Thanks, Mike. This was truly fabulous. So I am curious about whether you guys have thought, especially as you're starting to scale to very, very low metallicities, if you've thought about basically the impact of different elemental chemistries might have on some of these physics might be more tied to elements that have longer delay times versus shorter delay times. And I'm just curious if you guys have like a multiple element chemistry and whether anything scales with something other than metallicity or if it scales with like any sort of specific elements, or if you guys have thought about it at all.
We haven't thought about it much. We've certainly discussed it because, of course, yeah, not everything is just a perfect rescaling of, the Asplin solar abundances. But that is all we have been doing essentially, is just take that and scale it to, 10% or 1%. Different elements are responsible for different ISM processes. So one can imagine that if you vary those ratios, then things may play out differently in terms of the properties of your dust or your fine structure transitions for cooling, and of course your stellar abundances as well. But yeah, we haven't really opened up that can of worms.
This is great. I was just curious how much variation you might see in the turnover mass and what processes seem to control that the most.
Yeah, great question. So the short answer is there's not a lot of variation in the turnover mass because it doesn't really have a large range that it can vary over. And the reason for that is that there's kind of a lower bound here where you have this kind of low mass cutoff set by dust radiative processes. So, I can kind of make this slide around, but in practice, in typical Milky Way conditions, this is already pretty close to this. And the way to make this slide around is basically to have denser clouds that have smaller Jeans mass. But again, once you have a sufficiently low kind of cloud scale Jeans mass, you just hit this opacity limit. So that's kind of my cartoon picture in my head for why we shouldn't expect a ton of variation. I think the one way that I can actually make this turnover somewhat large is to take a low density and low metallicity cloud. And the reason for that is that cloud will be relatively warm, and relatively diffuse, which means a large Jeans mass. And then you can kind of make that turnover mass like a factor of 2 or 3 larger than sort of typical IMF. And that is what we find in STARFORGE. Unfortunately, it hasn't really been possible to directly test that with any observation I'm aware of. But yeah, so you have these different processes that set these different mass scales, and they kind of work together to get you the final IMF.
Any more questions?
Just continuing on the question of IMF variations, there's been claims at least that the low mass end of the IMF slope varies as a function of environment, or I guess mass with the galaxy, or velocity dispersion, or anyway, some tracer. So these are not the processes you identify. So what is your take on this? Is any of these driving some of that, or?
So what particular observations are you referring to?
Well, estimates of stellar masses from, I think, spectroscopy, basically assuming that those bottom heavy IMFs in elliptical galaxies.
Right, that stuff. Okay.
Yeah. And I think there's been some other, but I haven't followed it very closely.
Yeah, and the short answer to that, and I'm sure Drew could say a lot more about this. I don't have a short and sweet explanation for those observations, honestly. Like, I know that the sort of classically quoted result is like a slope of like -3 in this certain range, which like we definitely don't see anything remotely like that in the scope of STARFORGE. One thing to note is that the IMF you get in your galaxy is the result of stacking the IMFs of every star cluster that formed in it. And the result of that stacking does not have the same shape as the original cluster scale IMF. So that may also affect the way that we get from kind of the cluster scale IMF to the galaxy scale IMF. But I honestly consider that whole space of observations to be still an interesting open problem for the field.
Thanks.
Any more questions?
That was a super cool talk. Thanks. I was wondering, to what degree would you call STARFORGE fully hydrodynamical collisional code?
Fully hydrodynamical collisional. So do you
Yeah, I
mean
guess-
collisional in the sense of stellar dynamics, or collisional in the sense of like microphysics?
Yeah, so I guess I'm thinking about like late time evolution of star clusters.
Mhm.
And of course, you've talked a lot about some cool stuff on the early time evolution of star clusters. But like if I wanted to keep evolving the stars clusters, then like what sort of physics is needed in order to like fully capture that? How much of it is already in there?
Yeah, I mean the key physics are just the dynamics plus the stellar evolution, and like we model those to some degree with StarForge enough to do what we're trying to do, which is get to like the 10 million year mark. But there are better tools for going farther. So what, for example, Juan, he takes the output of StarForge and plugs it into n-body 6, which is, you know, this sort of ancient code that's been essentially in a continuous line of development for more than half a century, and is specifically designed for these sorts of longer term integrations. And like basically the way that it will do the integration, it will be more accurate and specialized to the task, and it will also have more sophisticated treatments of the stellar evolution than the relatively simplistic things that we do just to get the feedback right.
I see. Cool. Thanks.
All right, any last questions? We'll do one more.
Okay, I hate to ask this, but and maybe maybe I don't hate to ask it, but what so what can StarForge say about like stellar multiplicity and fragmentation into you know, and how you know what would it need to take into account to make predictions about like binary fraction at the high mass end? Slash, can you speculate on how that might change things about evolution, even during accretion, etc.?
Yeah, great question. So the answer is we can say some things about multiplicity, but not all. So we actually have a paper out, Guseyanov 2022, looking at multiplicity in various simulations. And if you have, for example, say a period distribution for the stars, then you'll get something that looks kind of like what the observations are doing, until you reach a certain scale where you get this big pileup and then nothing at smaller periods. And the reason for that is that we are applying a softening scale to our stellar dynamics, and we're also not resolving the gas physics on these smaller scales that would produce these shorter period binaries. So we can do things like Gaia wide binaries all day long, and those actually look pretty good. But the kind of frustrating thing is we can't really do the sorts of really close binaries that actually do really interesting things from a population synthesis standpoint, for example. And that's just due to our limitations in numerical resolution. But we can say some things like, for example, one can imagine that if we're only resolving down to a certain scale and finding that like all of our massive stars are in binaries, even without the disk fragmentation that we're missing, then adding in the disk fragmentation, that's not going to change that. It's just going to make it even more so. So, there are things you can say just from the sort of wider binaries and the trends that you find there. And things like the fact that it is very, very difficult for O stars to not be in a binary, even if you're not resolving the small scales. So like, you know, you wouldn't want to use a model where like 10% of your O stars are in binaries, for example. But of course, we knew that.
All right, let's thank Mike again.
Thanks, everyone.